In this video, we're going to look at some more tools that we can use to prepare more complicated molecules. And it's just going to be a few examples of reactions of alcohols, namely oxidation of alcohols. Okay, so what we want to do is talk about how to oxidize an alcohol. And so by oxidation, what I'm saying is that we are going to take our alcohol through a series of steps where, and the steps are oxidation, where the first oxidation is going to convert this first molecule into a carbonyl. And that's going to be the focus of this lecture. Okay, so I'm going to put organic 1 to separate it from the second oxidation step, which could take, in this case, an aldehyde into a carboxylic acid. Okay, so in this is kind of like the sequence of events where you could oxidize an alcohol. You first convert the alcohol into a carbonyl, and then the carbonyl into, maybe you recognize this is a carboxylic acid. And I guess I'll erase this organic 1. We do need to kind of be aware of both of these oxidation processes. Now, what I want to take a second to kind of bring up that I think is interesting is when you, not you, but when someone consumes alcohol, like ethanol, we actually have to go through this process to get the alcohol or get the ethanol out of our bodies. Okay, so let's kind of go through briefly ethanol metabolism. And sorry, I got distracted there for a second. I was just making sure I had the names of the players that are used to allow us to excrete and metabolize ethanol. So when ethanol is consumed, we have to recognize this is a toxic molecule. There really, aren't safe amounts of ethanol that can be, well, you can consume ethanol to levels where you would survive the consumption, but there's not like a healthy amount of alcohol to consume unless you don't have any other source of water. Anyway, neither here nor there. Okay, so it's toxic, causes drunken feeling. And so as a result, people, whatever the side effects of being drunk for a certain individual are, this can be appealing to people. And so people consume ethanol. When ethanol is consumed, it needs to be metabolized. It can't be readily excreted as ethanol. It needs to be handled. And it's handled actually fairly quickly using an enzyme called alcohol dehydrogenase. Dehydrogenase. Okay, so that's a catalyst. Enzymes are just biological catalysts. So you have some floating around your body. When you consume ethanol, to avoid always kind of succumbing to ethanol poisoning, alcohol poisoning, your body starts to metabolize, break it down so that it can be properly excreted. The interesting thing is that when ethanol is metabolized, we get to the first step in the metabolism involves the oxidation of ethanol to this aldehyde, and this is acetaldehyde. Acetaldehyde is the hangover molecule. When someone has this floating around in their body, it can cause things like nausea, light sensitivity, headaches. Our body puts a lot of effort into kind of diluting this, so people become dehydrated as we use a lot of water to kind of decrease the concentration of this floating around. It's overall not great. It's toxic for us. Okay, so that's not good. But there's another enzyme that can come along, and that other enzyme is just generally called an aldehyde dehydrogenase or an aldehyde oxidase. So this is like enzyme 2. These are separate catalysts. It's not one enzyme that's doing both jobs. Each oxidation step gets us closer to this molecule, acetic acid. Now, acetic acid has the name acid in it, but it's not as strong of an acid as like hydrochloric acid and that sort of thing. So our body can certainly handle some of this floating around as a result of metabolizing acetaldehyde. Now, obviously, if you have too much acetic acid or too much of anything really, but acetic acid is not water. You can't just like drink acetic acid. But acetic acid is vinegar. And while it's bitter, it's actually, it can be excreted and managed by our body fairly effectively. So in low concentrations, and again, I'm not saying chugging vinegar, but in the concentrations that you would get from ethanol metabolism, this is easily excreted. Okay, so on the surface, what this suggests is that the consumption of ethanol causes someone to have some fun. Okay, all right, they're drunk. Many people like to be drunk, whatever. Okay, weird thing to say by a professor, but you get what I'm trying to say. There's some appeal to getting drunk. So people consume the ethanol. No big deal, right? I mean, ethanol is toxic. You don't want it around, but it will be excreted by vinegar or as vinegar, which sometimes is pretty good for us. The issue is we go through this aldehyde intermediate. Well, it's kind of annoying. It'd be great if we just didn't have hangovers. Why don't we have hangovers? Well, the problem has to do with a concept called flux. And so the flux, or sort of rate of metabolism, is hilarious. At least, I mean, you gotta have fun. It's the rate of metabolism is such that ethanol oxidation is fast, but acetaldehyde oxidation is slow. And this is oxidation is slow. Now, I mean, it's kind of funny. Humans can actually process ethanol fairly quickly. We have a lot of alcohol dehydrogenases. In some parts of the world, people have more than others, and they're able to kind of process the alcohol even more quickly. But then the aldehyde dehydrogenase, we don't have as much of. It's a bit slower of an enzyme. And as a result, acetaldehyde kind of sits around in our body for a while before it's properly and fully oxidized and easily excreted as acetic acid, which means when they say the only cure for a hangover is time, they really mean it. We have to let that chemical reaction occur so that we can excrete we can excrete the acetic acid and completely rid ourselves of those two carbon atoms to get rid of the burden. Anyway, the focus of today's lecture is chemistry related to the oxidation of alcohols. There are a few approaches. There are many thousands of approaches to oxidizing alcohols, but the general approach is the same. We want to get the alcohol to a carbonyl or a carboxylic acid or some variant thereof. So the two approaches I want us to worry about in this class are not the best. And by not the best, I mean not the best environmentally. They're actually quite efficient at oxidizing alcohols, but they're environmentally the opposite of benign and very pollutive, and we've spent a lot of time trying to replace them, and we've done okay. But definitely these were the go-to approaches, sadly, in like the 70s and 80s in industry, and there was a huge amount of environmentally hazardous waste. But the lessons learned in the approach regarding the approach of oxidizing alcohols are still valuable to at least see from a strategic standpoint. Okay, so again, I'm not advocating for these approaches. I'm just saying these are some good approaches to start with as you're learning about oxidizing alcohols. When you actually want to go in the lab, let's do something different. Okay, so two approaches are the Jones oxidation and PCC oxidation. Now, these are both problematic because they involve chromium salts where chromium is in a high oxidation state. Chromium is Cr, by the way. So that's not good, because when chromium is in a high oxidation state, it's bad for the environment and the humans that use them. So not only is it just bad for the environment, but it's also toxic, carcinogenic, that sort of thing. We've replaced these methods, but instead of kind of overwhelming all of us with all the multiple approaches to oxidizing alcohols, let's just stick to, and if we look at the first example, we started with some enzymes. It doesn't, for the most part, doesn't get too much greener than using enzymes. And we've gotten good at using enzymes to do these industrial oxidation processes. So we've gotten very green. We have a long ways to go, don't get me wrong, but we're not using chromium anymore. Chromium is a good first place to start. I probably have said that enough. Okay, and humans. Okay, so chromium, we have chromium in the high oxidation state. Now the Jones reagent for the Jones oxidation, it's not really a reagent, it's more conditions, but it's H2Cr2O7, or the salt of this, Na2Cr2O7, and a combination of the salt plus H2SO4. So this is an acid that has all the toxicity and carcinogenic aspects that chromium atoms have. Or we can use the salt and then just convert it into the acid by mixing in a strong acid like H2SO4. So these are the Jones conditions. So when you see either of these sets of conditions, I want you to think Jones oxidation. So this is the Jones oxidation, and it oxidizes alcohols in the process that we kind of talked about. What I want to do is just mention an issue with the Jones oxidation. The Jones oxidation cannot be used to make aldehydes. Because aldehydes will over-oxidize. Okay, so what do I mean by that? Let's say we have some alcohol here, and I treat that with the Jones oxidation condition. So I'll just put Jones with a bracket. So this implies the Jones oxidation. Under the Jones oxidation conditions, you will form the first oxidation process. And in this first oxidation process, we're converting this carbon-oxygen, I'm going to pick a different color, converting this carbon-oxygen single bond into a carbon-oxygen double bond. That's what the oxidation process is. But then this intermediate is an aldehyde. And the aldehyde is known to continue to react. And you can't control this or get it to stop, so you can't make the aldehyde. Instead, you over-oxidize the system. Now, the first oxidation is the formation of a carbon-oxygen double bond. The second oxidation is the insertion of an oxygen between a carbon and hydrogen. So this is the product that you would obtain, the carboxylic acid. And this, again, is what is formed. This is quite interesting, because how do we then stop at the aldehyde? Okay, that's an important question. Well, we use an alternative reagent. So to stop at the aldehyde, and an aldehyde, remember, is a carbonyl with a carbon group on one side and an H on the other side. To stop at the aldehyde, we want to use PCC. So PCC is a new oxidizing agent called pyridinium chlorochromate. Okay, so there's that chromate term. This is another chromium-based oxidant, again, not good for the environment, and one to be avoided whenever possible. However, what's different about this than the Jones conditions is that there isn't any water present. And as a result, we're actually able to stop the oxidation at the aldehyde. It's actually the water in the original Jones oxidations that facilitate the subsequent oxidation of the alcohol, or excuse me, the aldehyde to the carboxylic acid. That's chemistry for that particular event. The oxidation of an aldehyde to a carboxylic acid is a topic for organic chemistry too. So in pyridinium chlorochromate, we have this salt. So this kind of sits together as a salt, and it's called the PCC salt, where PCC stands for pyridinium chlorochromate. It's just another chromium-based oxidant. The difference is because we don't have water present, when we add PCC to a primary alcohol, we will see the reaction stop at an aldehyde. Let's look at that. So I've drawn a primary alcohol before, and it's a primary alcohol because the carbon attached to the OH group, to the hydroxyl group, the thing that makes it an alcohol altogether, has one substituent. So this is a primary alcohol, and I think we went over that in lecture 105 if you need to review that. So the issue that I'm bringing up is that when we use the Jones oxidation conditions, we don't get the aldehyde intermediate. Maybe I'll make that red. We don't get the aldehyde intermediate. Instead, we form the carboxylic acid. But maybe you want the aldehyde. Maybe you want the carboxylic acid. I don't know. I'm just trying to give you some options here. But if you do want the aldehyde, you have to change your reagent from the Jones oxidation conditions that contain water to PCC. When we use PCC, then we have formation of the aldehyde, but not formation of the carboxylic acid. So anytime you can have more options, it's always a good thing. And these are the two oxidation reactions I want us to use. We'll learn about some more in organic chemistry too, like the Swern oxidation. We'll actually do a bleach oxidation in the lab. And then in advanced organic chemistry, we'll talk about enzymes that can be used to facilitate the oxidations. But for now, it's these two harmful chromium-based oxidation conditions. So let's practice this a little bit. So let's say we've got, let's take ethanol and we will react it with Jones and PCC. Well, this is a primary alcohol. It has these two. So what I'm going to do is just kind of cross out the H and draw a double bond, and that's my product. So if you're worried about drawing the product for the oxidation reaction, it's just you cross out the hydrogen on the OH and draw that second bond. We don't normally draw the implicit hydrogen, but I guess I have to cross that out too. And that would be the product for the PCC reaction. PCC reaction does not over-oxidize. That forms an aldehyde. Now, as we just mentioned, if you use the Jones oxidation, you will indeed form the aldehyde intermediate as an intermediate, but it will continue to over-oxidize to form a carboxylic acid. So the product, if you use Jones on a primary alcohol, you need to propose the carboxylic acid as a product. And you can make a note, though, that it does go through the aldehyde intermediate. We just can't shut the reaction down or control it in a way that we wouldn't get a mixture of products. With PCC, though, we do stop at the aldehyde. We don't see over-oxidation to the carboxylic acid. And so the correct product is where you remove the two hydrogens, draw the second bond between the carbon and the oxygen. Now, what about for a secondary alcohol? Well, for a secondary alcohol, we're going to have two substituents attached to the carbon bearing the OH group. So here's my secondary alcohol. I'm going to use Jones and PCC. Now, in the case of both of these, we will oxidize the alcohol appropriately. You could show that by drawing, if you want to draw that hydrogen, you could show the two hydrogens that are being lost in the double bond. We'll oxidize this alcohol to the corresponding, in this case, a ketone. Ketones have carbons on either side of the carbonyl. And we're done with PCC. Now, what about Jones? Can we over-oxidize? Turns out we cannot, because you can't add an OH group to this molecule. And as a result, you do not form some sort of carboxylic acid intermediate. I mean, look at this carbon. It already has 5 things attached to it if we add an additional OH. Whereas in the overoxidation of the aldehyde, we actually convert this CH, the aldehyde CH, into a carboxylic acid. Okay. Now, I like thinking about the octet in the case of the secondary alcohol. There's actually some other reasons why it doesn't over-oxidize. But the point is, with secondary alcohols, the task is easier. We get the same product with either of our oxidation conditions. However, if we move on to the tertiary alcohol, tertiary alcohols are alcohols where the carbon bearing the OH group has 1, 2, 3 groups attached to it. And so what we need to do is consider both conditions. And this is another case where both conditions will give us the exact same product, which is no reaction. You cannot oxidize a tertiary alcohol because you would break the octet at the carbon atom that gets oxidized. And as a result, I'll stick with red, there's no reaction. So NR stands for no reaction. Okay, so these are the two oxidation reactions. They basically do the same thing where you convert the carbon-oxygen single bond in an alcohol to a double bond that allows you to make carbonyls, which we'll see being useful in the next lecture. The things to make note of are that with the Jones oxidation reaction, which are very convenient conditions, aside from their harmfulness to the environment, you can oxidize anything, but you sometimes over-oxidize things like aldehydes to carboxylic acids. You might say, well, why don't I want to use the Jones reaction in every case? Well, the reason why you don't want to use the Jones why wouldn't you want to use the PCC oxidation in every case? Then I don't have to worry about this. Well, the reason for this lesson and this lecture on oxidation chemistry isn't to give you the most robust and up-to-date oxidation conditions. It's rather to get you thinking about what can happen during an oxidation process. You can oxidize an alcohol to a ketone. You can oxidize it to an aldehyde, but be aware, aldehydes are actually prone to over-oxidation to carboxylic acids. That's really a nice take-home message and something that's useful going forward. So in the next lecture, we'll look at how we can use these reactions to make structurally complex molecules by having sequential Grignard reactions. Do one Grignard reaction, oxidize your alcohol product to a carbonyl, and do a second Grignard reaction. Okay, anyway.